Welcome to our tutorial of ProfLearn YouTube channel. In this particular video, we're going to have a discussion on photoelectric effects, a topic of physics, IAL, EdExcel, Unit 2. So we're going to see what are the possible questions that have been asked and what are the possible ways in which questions can be asked in this coming exam. If you are new to ProfLearn YouTube channel, consider subscribing so that anytime we are going to upload a tutorial, you'll be notified. And also I need to bring you to our attention that you can be able to check in our Patreon page. There's a link in the description so that you can be able to access some of these notes and also the PDF I'm working on. Now we need to go and dive in so that we can be able to get started. In this particular video, we are going to look at one of the questions that was tested and what is the best way to approach it. So the first thing that we really need to understand is that photoelectric effect is a phenomenon where when light or radiations of a particular frequency are directed or shown on a metal surface, electron will absorb the energy and they will be dislodged and they'll be able to move away from the surface. One of the things that you need to understand is the definition of the work function, and we're going to define work function as the minimum energy required to dislodge an electron from the metal surface. One energy is not enough to dislodge that electron from the metal surface, then that electron cannot be able to absorb that amount of energy. So if the energy is more than what is required to dislodge, then the other part of the energy is used to accelerate the electron away from that surface. So that other extra energy will be used as kinetic energy for the electron to move away. So we are told that ultraviolet UV section of electromagnetic spectrum can be split into three parts known as UVA, UVB, UVC, and the range of wavelength of this part is given in the table from 200 to 280, 280 to 320, and from 320 to 400 nanometer. The minimum de Broglie wavelength of a released electron is 1.5 times 10 raised power -9. So deduce whether the ultraviolet light incident upon the zinc plate is UVA, UVB, or UVC. So the first thing that we were supposed to do, we want to basically what we need to do in order to answer this question is to work out and get the wavelength. Once you have the wavelength, you can be able to compare it against whatever values that we are having in this case. So de Broglie's formula or de Broglie's equation is usually lambda is equals to h over p, where this is Planck's constant and this is the momentum of that particular electron. So which means that if we want to calculate the momentum, we can be able to say momentum is equals to h over lambda. So which means we already know the wavelength, which is lambda, and then we know Planck's constant is 6.63 times 10 raised power -4 divided by the wavelength that was provided. We shall get the momentum of those electrons to be 4.42 times 10 raised power -25 kilogram meter per second. Once you have gotten that, you need to remember that momentum is usually mass times velocity. If you have the mass and the velocity, you can be able to get the momentum of an object. Now in this case, we need to know what is the velocity of these electrons. So already we have gotten the momentum, then we are going to divide by the mass of an electron, which is 9.11 times 10 raised power -31, and if you work it out, you are going to get your V being equals to 4.85 times 10 raised power 5 meters per second. That is the velocity of this electron. But we understand that kinetic energy is equals to half mv squared. So if we know the mass, we know the speed, we can be able to work out the energy at which the electrons were moving away. So we are going to relate that with this part that we have. This is going to be our kinetic energy on this part, but this usually represents the work function. But now the kinetic energy, we are going to get down here. You see we represent the kinetic energy of that. So we are told that or we know the photoelectric effect equation is that energy of a photon is usually work function plus kinetic energy, and already we know the work function was given there, right? So we want to know the energy of a photon, so we are going to take the work function that was provided at this given point plus the kinetic energy that we have gotten here. If we add them, we are going to get the energy of the photon. So which means that if we convert, or already we are given the energy in electron volts, so which means we are going to convert that particular energy we have there in we have to convert it so that we have the energy in joules, because our energy was in what? The energy was in electron volts. So if you take the value of electron volts, you multiply it to 1.6 times 10 raised to power negative 19, then it means we are going to have our energy now in joules. So once we have gotten our energy in joules, then we are going to add it to the kinetic energy we have gotten here, and that will be now the energy of the photon, because energy from this photoelectric equation, energy of a photon is equal to the work function of the metal plus the kinetic energy at which the electrons are going to move away from the metal surface. So that is exactly what we have done here, and we got our energy being equivalent to 7.95 times 10 raised power negative 19 joules. That is the energy of the photon. But we know energy is equals to hf. So basically we are trying to work out the wavelength. Remember, the objective is to work out the wavelength, and in that case f is usually speed of light over lambda, because we know hf energy is equals to Planck's constant times frequency. But the wave equation, we know that from the wave equation we know that f lambda will give us the speed of a wave. But in that case, we're going to use speed of a wave, because we are talking of electromagnetic waves. All the electromagnetic waves have the speed of light, which is 3 times 10 raised to power 8, and that speed now is c. So that's why you can see, instead of frequency that I'm having here, I'm going to replace with c over lambda, so that I can be able to make lambda the subject, and I was able to get my wavelength to be 2.5 times 10 raised to power negative 7 meters. Then if I want to convert this to nanometer, I'll divide the value I've gotten here by 10 raised to power negative 9, and that becomes 250 nanometer. So once you have this 250 nanometer, you need to go back now to the table, check which one is really where does 250 nanometer fall, in which part does it fall, where does it fall? If you look at that, it's falling between 200 and 280. So which means that this is UVC, and that becomes the answer for that particular part. So moving to the next part, moving to the next question, we are going to look at a scenario whereby a student was told that a student used a zinc plate and UV light of different frequencies in an experiment, and the student's graph of maximum kinetic energy of the released electron against frequency of UV light is as shown. So we have a graph drawn there, and we are told that Einstein photoelectric equation apply in this situation, meaning that HF is equals to work function plus a half mv squared. Now describe how the graph is not consistent with the values known for zinc plate, your answer should include part of some of the calculation. So the first thing that we need to understand is that if at all the work function is 4.30 electron volts, then we can be able to, because we know work function is usually drawn like that. That's a symbol for work function, is usually HF naught, where F naught is the threshold frequency, and threshold frequency is the minimum frequency of irradiation below which no photoelectric effect that will take place. So if we are having work function here, we can be able to work out the threshold frequency, and in that case we're going to say 4.3 times 1.6 times 10 to the power 19. I'm multiplying this so that I can be able to convert it to joules. This is energy in electron volts. So the work function in joules is going to be 4.3 times 10 times 1.6 times 10 to the power negative 19 is equals to HF. H is the Planck's constant, but F is the threshold frequency. So in that way, if you work out the threshold frequency for zinc, the threshold frequency for zinc, we are going to get the answer being 1.04 times 10 to the power 15 hertz. 15 hertz. But if you look at the threshold frequency of the graph is 7.5 times 10 to the power 14. So you can see the threshold frequency that is shown here is 7.5. So which means that the graph is not consistent for zinc. This graph is not consistent for zinc. So if it was for zinc, and we are told for zinc the work function is 4.3 electron volts, then if you work out the threshold frequency and the threshold frequency that is shown on the graph should be the same. So we can say the graph is not consistent. Something else that we need to put into consideration, because we were supposed to identify two ways the graph is not consistent, we need to understand that I have mv squared, actually that is what's on the y-axis. I have mv squared and against frequency. So we know I have mv squared is equals to hf, yeah, hf minus work function. Now, if you relate this equation with the equation of a straight line y equals mx plus c, this is the y value on the y-axis, and since the graph is plotted against frequency, this is the x values, then h is going to represent Planck's constant. So what does that mean? If you work out the gradient of this graph that is drawn there, should give you Planck's constant. All right, so if you work out the gradient of this line and you find it's equal to 6.63 times 10 to the power negative 34 joules second, then it means the graph is consistent. But when I try to work out the graph, remember gradient is usually rise over run. If I worked out that, I got my value to be 2.13 times 10 to the power negative 3 joules second. This value is not is not anything close to 6.63 times 10 to the power negative 4, which is usually Planck's constant. So the gradient is not equal to Planck's constant. So the graph is not consistent to whatever zinc plate that we are told. So you could work out threshold frequency, you check whether it's the same as the threshold frequency shown on the graph, and also work out the gradient, and in that way you are able to show that. So basically that's what you are supposed to do. We need to move to the next part and get to see exactly what you are supposed to do. If you are new to ProfLearn YouTube channel, and if you are finding value from this particular video, consider subscribing so that anytime I'm going to do more tutorials, you'll be notified. Remember to check in the description a link to our Patreon page where you can be able to access some of this particular PDF. So we need to move right to question number 2. We are told, in an experiment to demonstrate photoelectric effect, ultraviolet light is incident on a metal plate. Photoelectrons are released from the plate with a maximum speed of 3.51 times 10 raised to power 5 meters per second. Calculate energy of this photoelectron in electron volts. So if they are moving at that particular speed, then we need to work out the kinetic energy in order to get the energy of these photoelectrons. So if you work out kinetic energy, we know kinetic energy is a half times mass times the speed squared, and the mass of an electron is 9.1 times 10 raised to power negative 31 times the speed. Remember to square that, and if you work it out, you are going to get 5.6 times 10 raised to power negative 20 joules. That is energy, kinetic energy of these electrons in joules. But we are supposed to get our answer in electron volts, so you are going to take that value you have there, divide it by 1.16 times 10 raised to power negative 19, and we shall get our answer equivalent to 0.35. Now the table shows typical values of work function for 4 different metals, and in that case you need to remember the photoelectric effect equation. Energy of a photon is equal to the work function, and we have said work function is the minimum energy required to dislodge an electron from the metal surface, and then plus kinetic energy. So important definition you need to understand in this particular topic. So you need to understand threshold frequency as the minimum frequency below which photoelectric effect will not take place. You need also to understand that the threshold wavelength, and this is the maximum wavelength above which no photoelectric effect will take place. You need also to understand the definition of the work function. And on this particular question, give it a try so that you can be able to leave a comment on which metal is the best in this particular case. Photoelectrons are only emitted from a given metal surface if the frequency of the incident radiation is above a particular value. We are supposed to explain why is that case. So we need to understand that each photon only interacts with an electron. Each photon, each radiation, each photon, each packet of a photon only interact with one electron, and the electron absorbs that energy of the photon. There is a minimum amount of energy required to be absorbed for the electron to be dislodged from the metal surface. So if the energy is not enough, then that photon will not be absorbed by that electron. So something else we need to remember, that higher photon energy is related, higher photon energy is related to the high frequency. Energy of a photon depends on the frequency. So the frequency of radiation has to be above a particular value. If energy has to be above a particular value for an electron to be dislodged, then it means that for an electron to be dislodged, it also means that frequency must be above a certain value, since the energy depends on frequency, right? And this amount of energy it should be above is what we call the work function. A student makes the following statement: it does not matter what value of work function is for a particular metal, photoelectrons can always be released if the intensity of the incident light is high enough. This statement is very dangerous. This statement is not true. Intensity is related to the number of photons per second, and intensity does not affect the energy of the photon. So intensity will only affect the number of electrons emitted per second. So if the energy of a photon is less than the work function, however many photons you can have, however high intensity you can have, no photoelectric effect will take place. So you have to be very careful with this statement that has been made by this student, so that you are not going to make the same mistake during your exam. So we need to move also to question number 3, get to see what the question is about. We are told that light of wavelength lambda traveling at the speed of c is incident on metal surface. Photoelectrons are emitted from the metal surface with a maximum kinetic energy. So we are told that a graph of 1 over lambda against 1 over 2 meter 1 over 2 mv squared is drawn. So where is this graph coming from? So if we can look at this from the perspective that hf is equals to the work function, and which is hf naught plus a half mv squared. This graph that this equation that we have here in terms of wavelength, it can be written as also h c over lambda is equals to, let me just use the symbol for work function, plus a half mv squared. So I want to have only lambda on one side, then it means that I can be able to say 1 over lambda is equals to, I'll take the whole of c hc, I divide it all through, so I'll have 1 over 2 mv squared plus the work function divide by hc divide by hc. So which means that since this graph is 1 over lambda against a half mv squared, then I can say this is actually 1 over lambda is equals to 1 over hc 1 over 2 mv squared plus work function over hc. So, and I want to relate this equation with the wave equation. So if I relate this equation here with y is equals to mx plus c, you can see this is the gradient, and the gradient of this graph that we have here is going to represent 1 over c, 1 over hc, and the whole of this part, which is the y-intercept. So if you take the y-intercept of this and equate it to this, we are going to have another equation. Now, which of the following show the gradient of the graph can be used to determine Planck's constant? How can the gradient be used to determine Planck's constant? So it means the gradient of this graph, gradient, and our gradient is this part here, 1 is equals to 1 over hc. So which means that our gradient, if we want to find Planck's constant, we are going to rearrange this equation, and it will become Planck's constant is equals to 1 over gradient times c, and if you can be able to work it out, you can see it's well seated here. Planck's constant is equals to 1 over c times gradient, which is the same thing that I've highlighted at this given point. Question 4, we are told that a photomultiplier is a device that can detect very low intensity light. In a photomultiplier, a metal plate called a photocathode is connected to the negative terminal of a power supply. Electromagnetic radiation is incident on the photocathode and can cause photoelectric effect. And photoelectrons are emitted through thermion emission. So meaning that if you have a metal surface and then you have incident radiation on this one, it means that this electrons on the metal surface are going to absorb the energy of the photons, and then they are going to be dislodged. So describe what is photoelectric effect. Photoelectric effect is a phenomenon where when a radiation is directed or is incident to the metal surface, electrons of that metal will absorb the energy and they will be dislodged from the metal surface. So basically that's what I'm trying to illustrate here, that we have a radiation and the radiation has energy, and energy of a radiation is usually hf, Planck's constant times the frequency of that radiation. If the energy supplied by this radiation is more than the work function, then that electron is going to be dislodged and it will move away at a given speed. Yeah, so meaning that part of this energy of the photon will be used to dislodge. That amount of energy that is used to dislodge an electron from a metal surface is called work function. Part of the energy that is remaining, that was in that photon, that the energy that's remaining after dislodging, is used as kinetic energy for the electron to accelerate away from the metal surface. So we can say a photon, when a photon is incident on a surface, is absorbed, the electron gains energy and they are emitted or released from the metal surface. The photomultiplier can only detect electromagnetic radiation that cause photoelectric effect. Explain why photomultiplier cannot detect some frequency of electromagnetic radiation. So in this case, a photomultiplier only detect when photoelectric effect has occurred. So if we have those radiation which have less frequency, which have frequency below the threshold frequency, then no detection will take place because no photoelectric will take place. So in that case, we can say to cause photoelectric effect, the energy must be greater than the work function. And since the photon energy is proportional to the frequency, so photons below threshold frequency cannot cause photoelectric effect. Hence, they cannot be detected by the photomultiplier. Right, so we reached at that particular point whereby we now need to move to calculations. And in this case, we are told visible light has a range of wavelengths from 380 nanometer to 700 nanometer. The work function of a material used to make a photocathode is 1.48 electron volts. Deduce whether the photomultiplier can detect all the wavelength of visible light. So we know work function is equals to h times the photoelectric, the threshold frequency. And threshold frequency is equal to the speed of light over the threshold wavelength. So in that case, we can be able to use this formula in order to work out the threshold wavelength. And we are using the work function. We have to multiply this by 1.6 times 10 raised power negative 19 so that we can convert it from electron volts to joules. So if you work out the threshold wavelength, if you work out the threshold wavelength, you are going to get it as 8.4 times 10 to the power negative 7. So all the wavelength, because we have gotten that, we can be able to convert these threshold wavelength. This is in meters, we convert it to nanometer so that we can be able to compare it against the values that were here. So if you work it out, you see it will be more than this, and that's going to be 840 nanometer. You can see now our value that we have gotten is more than the nanometer. So which means, so all wavelength of visible light can be detected in that case. In the photomultiplier, the photocathode and several atom plates are in a vacuum as shown there. And we are told that an electron is emitted from the photocathode at a speed of 1.35 times 10 raised power 6 meters per second, there's a potential difference of 108 volts between the photocathode. So we are supposed to calculate the kinetic energy of the electron with the first metal plates. So the first thing that we can do, we can be able to work out the kinetic energy first because of this speed that we are given here. And if you work out the kinetic energy, you are going to get the energy to be 8.3 times 10 raised power negative 19 joules. We need to remember also that the potential difference is equal to the work done to move a unit charge, right? Work done per unit charge is potential difference. So if we want to know work done, we can take the potential difference times the charge, the charge of an electron, remember? So work done is equal to the amount of energy transferred. So work done is equal to QV. So we are going to, using this potential potential difference, which amount of energy that is applied to this electron, right? So which means we can be able to say the charge is 1.6 times 10 raised to power 19 times the voltage, which is 108. Working it out, we're going to get our value equivalent to 1.73 times 10 raised to power negative 17 joules. Now, since already there is energy supplied on this electron, and also it was having kinetic energy of 8.3 times 10 to the power negative 19 joules, then it will mean that the final energy of this electron at the speed at which they will be, the energy they will be possessing as they are accelerating, is going to be the sum of this energy and this kinetic energy, and you get the total energy to be 1.813 times 10 raised to the power negative 19. So basically that's what you're supposed to do in this particular question. We are going to do part 2 of this photoelectric effect. So if you are not subscribed to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to do more tutorials and more topics on photoelectric effect and also Unit 3, you'll be notified. Remember to check how to answer question to do with Unit 3, that is practicals, practical skills. Check in the description. I've added a link that will take you straight to those tutorials and those papers which I've done. And don't forget to check in our Patreon page so that you can be able to download these papers. Without taking much time, I would like us to end our tutorial there. Don't forget to share this video to your friends. See you in the next tutorial.